In the previous video, we learned about the fundamental ideas of tokenizer. And we also learned how to build one of the most popular tokenizer from scratch, which is called byte pair encoding. And so if you haven't checked out that video yet, so I would highly recommend that you go first watch that video to understand the fundamentals and then come back to this, because this is going to be mainly focused on practical design decisions while choosing a tokenizer model. So while byte pair encoding model itself is so useful, as the language models became larger and multilingual, researchers developed that there were essentially two major problems with the vanilla version of the byte pair encoding model. And so in this video, we are going to discuss those limitations in detail, and we see how modern byte pair encoding model and one more library called SentencePiece help us in solving them. And along with that, we will also learn about some practical ways in which tokenizers help in making design decisions while building your own AI applications for real world use cases. Hi, my name is Josna and welcome to the Hidden Layers. And so suppose during training, our tokenizer has seen these words like play, playing and played. But at inference, we encounter a new word called playfulness. Now, a tokenizer which has not seen this word will mark it as unknown token. But in the previous video, we saw that byte pair encoding already has a way to overcome this issue by breaking it down into subwords. So far, so good, right? But there's still one edge case here. Suppose now we have a new input that the tokenizer has never seen before, like a new kind of emoji, or a new kind of Unicode character, or a currency sign which had never existed before. And since traditional byte pair encoding has a finite vocabulary, this again will fail for such scenarios and will mark them as unknown token. So in order to resolve such issues, a new variant of BP model was introduced, which is called byte-level byte pair encoding. So the idea was very simple. Instead of starting with all different possible characters as our base vocabulary, why don't we start with the bytes itself? Because at the end of the day, all the characters are stored in bytes. And since every Unicode character can be stored as a sequence of bytes, we essentially need only those 256 byte values as our base vocabulary. And that means that no matter what text someone types, whether it is in English or any other language, or a new kind of emoji, or a new kind of symbol that never appeared in training, the tokenizer can always fall back to bytes. And that's why byte-level BPE model has no out of the vocabulary problem. And that is one of the reasons why GPT models still use byte pair encoding. Now that was a problem which is solved. But there is still another problem. There is a major assumption on which BP models operate. And if you remember, in the last video, we discussed about something called as pre-tokenization, where we basically split our sentence into words, and so BP model assumes that a sentence is nothing but a sequence of words separated by spaces. So basically the spaces mark the word boundaries. So suppose the sentence, I am learning tokenizer. This is basically split into words first as part of the pre-tokenization step, and then it is tokenized into subwords. But now let's look at the Chinese version of it. It looks like a continuous stream of characters with no break for word boundaries. So then how can we split it into words? There is no way to do it using BPE. In fact, this is not just the case with Chinese language, but there is a whole lot of other languages where the word boundaries are decided by their own respective rules. So that means that BP algorithm is not so language independent, and we will need customized pre-processing methods for each of the languages, which is not so feasible. And so this is exactly the kind of problem that SentencePiece is designed to solve. And so the idea behind SentencePiece is, instead of extracting words out of a sentence using any pre-processing, why don't we treat the entire text as a raw input to the tokenizer? And so all the spaces which are present in raw text are replaced by a special kind of character, and so the tokenizer simply learns about the frequent pair of characters from the raw text. And so for Chinese language sentences where there are no spaces, that works fine too. And so it uses the same algorithm for every language. No Chinese or English based pre-tokenization step, and no different tokenizers for each language. Just raw text, and that's why SentencePiece is considered language agnostic. Now SentencePiece is not itself an algorithm, but rather it's a library, and it mainly implements two different tokenizers. First is our BP algorithm and second is Unigram. There are not much difference in the algorithm of Unigram from BP. So if you understand BP, which starts from a base vocabulary of all the possible characters, Unigram works top to bottom. So instead of starting out with a minimal vocabulary, it starts with a very large vocabulary and iteratively eliminate the tokens which are not very helpful in explaining the training data. So now you might be wondering why there are two different algorithms and how do we choose which one to use for our use case? Well, the answer is you don't generally choose a tokenizer if you're just using a pre-trained LLM model. So unless you're building your own language model from scratch, which is rarely the case, given there are so many capable models available today in the market, we generally stick to the tokenizers which are provided by the pre-trained model which we are using. Which means that if we are trying out any open source LLMs in our system, we mainly use the tokenizer which comes with it. We cannot replace it. Tokenizer and the model are trained together. Changing the tokenizer will completely change the token ID mappings in the embedding layer. But then why are we learning about tokenizers in so much detail? This is because even though we are not choosing tokenizer for model training, we are still responsible to take many engineering key decisions while building an AI application. And knowing about tokenizers in detail help us a great deal while building the AI application as well as debugging a problem. So let's understand it through a few examples. And so first is API cost. When we are using an LLM API, we are not built on the number of characters we are using, rather we are built on number of tokens. And that means that two prompts with similar length can have completely different costs depending on how they tokenize. So whenever someone asks why the token usage billing is so high, one of the first things I would look at is the token count. And the second area is the context window. We all know that LLMs have fixed context length, and like I mentioned before, it's not that the characters make the entire context length, but the tokens. And the number of tokens for a simple text with only words can be completely different from the content made up of JSON file or a Python program. So it's really important to focus on what really makes up your prompt. So in English, one token constitute on average zero point 0.7 of a English word. However, this token length could be much larger for a coding language and so might take up more tokens even with the same number of characters in the prompt. And now the third point is understanding the latency or how fast your model can generate the first output token. So basically suppose we have two different tokenizers and the one which takes more tokens to represent the same sentence than the other will have a longer token sequence. And this in turn leads to more attention and other calculations in the LLM, which means that it is going to be taking more time to generate the first output token and hence the latency will be higher. So understanding tokenizers may also help you in choosing one LLM over the other depending on the quality of their tokenizers. Then it can also help in other areas like prompt engineering. We can convey the same idea in two different ways, leading to two different number of token counts, and that can provide a metric to choose one prompt over the other. And so to summarize, even though we do not choose our own tokenizer, understanding about them help us in lot of different areas such as understanding the API cost, building better prompts, and then reasoning about which of the LLMs will be more suitable for our use case. And so that's why tokenizer is one of the most fundamental concepts in generative AI. And so that's a wrap for this video. We'll see you in the next one. Bye.